us.
All right, I'll try to be quick here, but I like one of those questions about the soils that you got, and you examined fungus in there, but let me tell you one thing, the soil is one of the most resilient of mediums you can find. And the reason they're resilient is because of a microbial symphony that happens at the back end, and that is what is enabling this interaction at a different scale. You're having multi-trophic interactions, and each of the dimensions, this is a dimension-based projection of soil, basically soil, but you can see if you break it down, you have these components that Tatiana mentioned, starting from sand, silt, clay, organic matter, and then you have plant root material, you have fungi that are entities in the microbial world, and then residues that are released by these microbes, like specifically bacteria release these extracellular polysaccharides that can also play a part in how these interactions occur, as well as colonies and the protozoan entities, which are microbial eukaryotes that coexist in the soils. And I just want to go one step back and look at a public press article that came out of an incident that happened in China in 2008, where they had a condition where babies were hospitalized with kidney stones and other kidney-associated damage. And they found out eventually that the reason for that poisoning that happened in these infants was because of a chemical that was fortified into the milk that the infants consumed. And that chemical was melamine that was used to promote higher protein content in the dairy that they consumed. And they didn't understand why these children were falling sick because of the material that they added to the ingredient. And what happened was eventually they did studies in animal models and also figured out that the reason they had that condition was because of a soil microbe that had permeated through the intestinal system. And it was metabolizing this chemical, causing a toxic byproduct. And earlier it was hypothesized that you would not have any soil microbe that can pass through the barrier of the gut, because we assume that we have gastric juices that are acidic. Obviously they are acidic, and they are impenetrable to these microbes that occur in nature and the soil. But it so happens that these guys are so resilient that they can even surmount that fluctuation in pH, which causes that acidity. And now they've shown that in animal models in a study that came out in 2013. And it's possible that these microbes can become smarter and adapt to this fluctuation in pH, which again gives us a take-home message saying that the food that we consume is also efficient on the basis of what microbes it associates with. And although you get food from different sources, you have organic produce, you have produce that comes from different other cultivation mediums where you have genetically modified mediums that can help in raising crops. But you need to find a delicate balance where you know the right set of microbes that can coexist or co-adapt to the food that you're trying to consume. And that is also something that's pivotal and needs attention. So we live in a microbial world, and it gives us context to think of ourselves when we associate ourselves with the microbes that inhabit us. And often there's huge press on this aspect of the human microbiome because of the nature of the microbes and how they determine our own health. We are starting to learn that the way we think or the way we react and behave is also influenced by the microbes that colonize our gut. And they are not only in our gut, but they're all over us. They're on our skin, and they're unique to each habitat. So the same thing holds good for the plant or for the crop that we raise. And these crops have their own sets of microbes that coexist in different habitats, starting from the soil that's around the root and the root itself. And there is an internalization process because there is recruitment of what microbes you find deep down in the soil. And there is a selection of the set of microbes that the plant wants to consume because it wants these microbes to aid in their physiological processes. And also eventually these processes will lead to the quality of the fruit or the vegetable it bears. So it becomes the question of asking whether these associated soil microbes are so critical that they can improve our longevity. If they are able to enhance our own thought process and things like our own immune system efficiencies, we have come to a stage where we're realizing that these microbes that coexist with plants, with the food that we consume, are going to be critical to what gets ingested and also what modulates our health. And if you go dig into that system that I just mentioned, if you can think of the soil deep down as a seed bank of these microbes. You have a combination of different microbes, those that are dependent on oxygen, those that are not dependent. They're differentiated as aerobes and anaerobes. And they all perform a specific function, and they are involved in chemical signaling that permeates information between the root tip on the root of the plant, and it communicates what set of microbes are needed for the plant. And using these chemical signals, they are drawn closer to this space and internalized. There is a process by which there is uptake. Cation exchange was talked about, and cation exchange becomes critical because you have these chemical signaling mechanisms that are influenced by these physical interactions that happen in soil, and that is also a means by which this internalization happens. And this step is very critical because it can help ward off other pathogens that can affect the plant in a normal field condition. And that is pivotal to see what happens below ground can affect the quality of a plant above ground. There is an interchange or an inter-exchange from below to above. And recently with research that's focused on microbes or microbiomes and examining the genetic composition of microbes on these hosts, there's been very interesting information coming out where we can draw parallels between our own gut to a plant system and examine the role of microbial sharing and the direction of which you take nutrients into your own human system versus how a plant system will behave. So it's a little bit of an inverse model where in the case of our own system, we consume food in the form of organic nutrients and water, and that is again digested through our stomach and gets into the gastric acidic zone, and that is also processed through the intestine, and then you go through the process where you have these microbes that coexist in the intestine and are helpful in processing the food. And there is again the variables that are governing what happens in soil, like pH. You have oxygen dependency, you have the density or the amount of abundances of bacteria that modulate how the digestion can occur. So that's the same analog that happens from below ground in a plant. So what happens below ground is you have excessive amount of bacteria that are recruited in, and then there is a filtration mechanism. There is partitioning that happens, and the plant is given information on what to take in and what not to, and that will determine the amount of minerals and ions and nutrient transfer through these physiological processes that influences the health of the plant. It's staggering the amount of information that's coming out of the latest approaches used in microbiome research, and it's great that we could work from end to end, starting from that grain of sand to what you get in the form of food. There is a connect, starting from an end to another end. And you want to also think about the materials that are there in soils. Basically, you have soils that are grown indoors, which can be dominated by what you call fungal members. And some fungal members can compete for space, and in that space they're going to stress the other members like bacteria. And I want to point you guys to another superstar in this microbial kingdom who are called archaea. And archaea are these transient members, which means they are like the fusion of bacteria and eukaryotes. We have recently found out that archaea are closest to Homo sapiens in terms of their genetic identity. And so these guys are also critical in agricultural soils, where they play a part in helping adapt to this pH fluctuation and also cultivation in highly saline environments. And we need to get more information on the ground to examine these soils and examine the microbial entities that coexist in different types of soils across continental scales. And even in a city like New York, you have these diverse boroughs that are determined by spatial or the location at which they are set up. So you need to take those informations into account and also plan for testing soils and look at the microbial information that you can derive from them. And I'll just let Tatiana or George follow up with the
I'm
soils.
going to let George take over.
Testing for those now?
Sure, I can take questions. Yeah.
Sorry. Are there any labs that are testing for those?
For the microbes?
And for the archaeal?
For the archaea, yeah. So we are also working on the green infrastructures in the New York City at Griffin College and also at the Advanced Science Research Center at City College. So there is a project where we're examining these green parks across the city and looking at these soil test beds and examining microbial communities that are occurring there, starting from bacteria, archaea, fungi. and looking at the roles of these communities in helping these test beds reduce the amount of toxicity that could set in because of combined sewer overflows in the city, which is a problem. And we're testing if we can find these resilient set of microbes that can help the site adapt to the toxicity and then bring it back to normalcy. So what happens is soil bounces back very effectively, even though it's given a huge amount of disturbance because of these microbes, they can switch back to a state they were in before. And there are methodologies in place where you can test for bacteria and archaea together. And for fungi, you need to have another test that is in place, but it is possible, and there's proven, there's literature published there, and it's totally doable.
As for labs in the city, I know we send out samples for our Dr. Moose lab sends out samples for bacteria strains.
Sure.
Cornell
University, Ithaca, they have a soil testing. They have a.
Some of them have that. Have you heard of Elaine Ingham?
Oh, yes.
So she's got that food soil web company, whatever, and I think, I mean, they have a really expensive test, but I think they have a not so expensive test also. You might want to check them out. We want to climb to that eventually, where we can do basic microbial analysis for certain soils, but we're just not there yet. But you can put that on the wish list. So just to go off of what Bharat said, and oh yeah, go ahead.
Can you go back to your first slide? Yeah, that's one. That one.
Yeah.
Just I wanted to write down that name there, cyanuric acid.
Yeah, cyanuric. Yeah.
Right. Produced from the fecal matter from rats.
Mm-hmm.
Okay. Now, just how important it is to keep rats away from, community gardens and urban gardens.
So the question is, you're asking if the rats can be a reservoir for the microbe?
Right.
Well, no, in this case, the testing was done in the rats that were used. So they used the rat models to test and ask the question as to whether Klebsiella terrigina, the soil microbe or soil or water associated microbe, was partitioning or getting transferred into the gut. So usually to test for microbiome-based analysis in human gut systems, they use analog models, which are rats or mice. Okay. And this was the test done on these rat models. So rats are not the carriers of Klebsiella terrigina, at least as far as this study goes. But in an urban environment, you do have them coexisting as part of the habitat. And they pose different set of health risks, but they do not have this thing on them. So that's not a cause of worry at this point. Yeah. Sure.
So I have a question about the health of soil microbes. And I've been trying to get rid of noxious weeds in the area by spraying industrial strength, like agricultural black plastic. It's been there for a number of months, and it's been very effective in eliminating the weed seeds that extreme heat during the summer seemed to sterilize the soil. But I was concerned about what it was doing to microbial activity and how quickly would the soil bounce back on the plastic.
So you said this is plastic. I mean,
Yeah.
and do you know the
It's kind of
composition
like
of
plastic mulch?
It's just mulch, okay.
It's like large sheets of essentially similar plastic to like contractor bags. I mean it's plastic. I don't know a whole lot about it, but it's
Great. So one reason plastic would work is because there's information out there that's coming out that says even soil microbes are transported from one habitat to another through these airborne loads, biological loads. You can call them aerosols. So aerosols are dispersed everywhere in the air. Even in this room, you have aerosols that are dispersed, and they can facilitate even the weed forming process. So you can have micro-scale aerosol formation, and pretty much I can understand if you have a plastic barrier, it's going to cut down that gaseous exchange that can influence the biological load from getting transferred from these microhabitats. And that is something that can be used as a control mechanism there. So, yeah.
So, I mean, I'm worried worried about harming beneficial organisms.
I just listened to a webinar on no-till agriculture where they used industrial plastic
Right.
over a whole season, and they found that it improved the soil. That it was a positive thing. That it did not hurt the soil. That it was a method that was used to improve the soil and a good way to get rid of weeds on large areas.
Maintains aerobic activity.
Sure.
So I'm not
No-till will,
creating a
yeah, no-till agriculture will maintain,
Will continue to.
maintain aerobic activity. And the other mechanism is to use cover crops. So you have cover crops that you can also cultivate alongside your plant, your crop of interest, where that cover crop can take in that, take down the competition that you can get from weeds and in the acquisition of nutrients. It can balance out the nutrient.
Right, because the excretions from both the plant and the microbes can help compete with
Right.
the weed, for example.
Right. So that's, and again for no-till, the advantage is you don't have as much of a cyclic exchange or a cyclic disturbance of these anaerobes resurfacing, exposed to the top layer of the soil. The top layer is very critical, microbially speaking. The top 6 centimeters is called the rhizosphere, which is very critical, and the way it's like a hierarchy. You need to have, in terms of these horizons, you need to have a set specific types of microbes that are coexisting in those locations. And when you shake them about, it's going to cause disturbance effects. But they will respond. They might recover through time, but that will take some time. So if you have a crop that you have only a shelf life of 60 days, you don't want that happening because the recovery will take more than that. So
when you consider this powerful weapon of microbes in soils, and you consider the fact that pH is kind of your steering wheel a little bit, and what happens chemically reacting wise, then if you think about the yield of your crops and the health of your soil and improving it and building it over time, you cannot diagnose your soil and say you're low in manganese